Now our desired quantity for this study is the probability of observing chorus, represented by mu, as a function of plasma pause extent, represented by L sub pp. The data that we have are true or false values, either chorus was observed or it wasn't, for a given epoch in which the plasma pause extent is known. The way we reconcile the fact that we want this continuous probability resulting from these discrete observations is via a method known as logistic regression. Logistic regression involves solving the linear model y equals x times beta. Here, y is a transformation of the quantity of interest mu, where mu is a probability and lies in the range from 0 to 1. The transformation shown here results in a variable y, which lies in the range from negative infinity to infinity, which is a typical output range of a linear model. The variable x, shown here, is a vector of different powers of plasma pause extent from 0 to 4th order, and beta are the weights which we are attempting to estimate. Using an iterative computational procedure, we can determine beta from our measurements. The results are shown here on the right, where we are plotting mu, probability of observing chorus, as a function of plasma pause extent. The results show that we see a maximum of chorus occurrence when the plasma pause extent is around L of 2.6, which is somewhat beyond Palmer's L shell at L of 2.4. Now, the fact that, this is also shown here in this model of the plasma pause, shown at 2.6, where we see the peak, and with Palmer shown here. Now, the fact that we observe this peak when Palmer is partially obscured by the plasmasphere indicates that the chorus propagation to the ground is most likely non-inductive. If the chorus propagation had been inducted, we would expect to see a peak when Palmer was exposed to the greater magnetosphere and the L shell of the plasma pause was below Palmer's L shell. Instead, since we see this peak when Palmer is still partially obscured by the plasma pause, this implies that inducted propagation is not taking place. We've also performed some modeling to confirm these observations. We modeled the 3 steps of chorus propagation from its source to the ground, namely its magnetospheric propagation, its propagation through the ionosphere, and then its propagation within the Earth ionosphere waveguide. The 3 levels of modeling which we use are ray tracing to model the magnetospheric path, which can be thought of as a method of solving Snell's law in a continuous, slowly varying medium. To model the attenuation during this propagation due to interactions of the wave with the warm plasma particles, we use a warm plasma damping code, which makes use of data obtained in situ of the ambient warm plasma densities. And finally, to model the attenuation suffered en route through the ionosphere and propagating within the Earth ionosphere waveguide, we use a full wave code, which is a method of solving Maxwell's equations in a stratified medium such as the ionosphere. So our goal for this modeling is a proxy measurement for the probability of observing chorus at Palmer for a given plasma extent. Our method is as follows. Rays are launched from 1,000 kilometers above Palmer Station, represented by this green triangle, spread in latitude and initial direction within the ionospheric transmission cone. Here I'm showing a series of rays which are colored by their initial latitude. The sum of the rays which reach the source region for chorus, which is shown here on the equator outside the plasmasphere, is referred to as the chaff, or chorus availability factor. Chaff is then our proxy measurement for the probability of observing chorus for a given plasma pause extent. Now, when this procedure is performed, rays tend to occur in a series of discrete families. Shown here on the left are 2 example rays from 2 different families of chorus rays. Here, we're showing the chorus propagation as if it has propagated from its magnetospheric source to the ground, although in fact we've modeled it in the reverse direction and then turned the ray around. The first family of rays is that which propagates from the source and penetrates to the ground via a direct path, and the second is one which has experienced a single magnetospheric reflection. Over the course of the ray's propagation in the magnetosphere, it is attenuated due to its interaction with the warm plasma particles, and the attenuation of these example rays is shown here as a function of time, where we can see that the second ray, that which has experienced one magnetospheric reflection, has been damped greater. Once the rays reach the ground, they are damped within the Earth ionosphere waveguide, shown here, where rays which must propagate further to Palmer from their ionospheric penetration point are damped more so than rays which penetrate to the ground closer to Palmer. Although these rays here are just two examples of the ray families, when you launch all of your rays for your simulation, all 1,040 rays, they are binned by radial extent and wave normal angle on a source attenuation plot, where wave normal angle here is defined as the angle between the wave's k-vector and the ambient magnetic field. Shown on the source attenuation plot are the two ray families from which these rays come, colored by their power in decibels. We can see that there are some interesting features of this plot, besides the fact that the rays are segregated into two families, namely that rays that originate at a lower radial extent, such as the ones on the left here, reach Palmer with a higher amplitude as a result of their shorter propagation path in the magnetosphere. The sum of the pixels of the source attenuation plot here is then our desired quantity, chaff, our proxy measurement for being able to observe chorus for a given plasma pause extent, such as L of 2.9 shown here. When this procedure is repeated for a variety of plasma pause extents, we get the resulting plot shown here, which is one of chaff on the x-axis versus plasma pause extent on the y-axis. We can then compare that plot to that resulted from our observations on the left, which is a plot of chorus probability of observance versus plasma pause extent. Now, when you compare these two plots, I hope you'll agree with me that the general shape is the same. Both originally start with low amplitudes for low plasma pause extents, increase in amplitude before reaching a saturation point, and then decrease in amplitude again when the plasma pause extent increases. Now, the differences between the two plots, the main one being the location of this peak, may be due to a variety of factors, including some systematic biases inherent in our plasma models, or the excessive smoothness of our cold plasma model, where we have not modeled the many density irregularities that permeate the magnetosphere due to their complexity. However, we can conclude from the fact that the general shape of the model and observation is the same, and the fact that the peak in occurrence probability is beyond Palmer's L-shell at 2.4, that the plasma pause does exert strong control over chorus propagation to the ground, and that the observed chorus is most likely non-ducted. So to summarize the talk so far, or summarize the talk in its entirety, because I'm almost done, the radiation belts are a region of trapped energetic particles in the Earth's magnetosphere, which pose a significant hazard to satellites and humans in near-Earth space. The structure of the radiation belts, in particular the slot in between the two belts and the outer radiation belt, are partially maintained by chorus and His emissions, which are two naturally occurring electromagnetic waves in the Earth's magnetosphere. For this work, we've used a neural network-based algorithm to automatically detect and categorize chorus and His emissions in our original broadband data. From the output of this automated detector, we've created an event database, which showed us that emissions are sourced during geomagnetic disturbances, but that ground observations are only effective during local night. Finally, we've shown that the plasmasphere plays a large role in dictating which chorus emissions will reach the ground from their magnetospheric source. And as a result of the control by the plasmasphere, we've shown that the ground stations can observe non-ducted chorus, which makes them much more effective than previously thought in estimating the magnetospheric distribution of waves, and in turn, the effect of those waves on the radiation belt particles. I'm going to flash this slide up here to impress you, which shows 3 publications relating to this work. And that brings me to my acknowledgments. I suppose no thesis defense stands alone and I have to thank a variety of people who have helped make this both a pleasant and, at times, an educational experience along the way. The first is my thesis advisor, Umran Inan, who really possesses an amazing knowledge, both of the field and of the mind of graduate students, that is really unparalleled and occasionally disconcerting. And I feel very lucky to have had Maria as my mentor. Maria possesses an incredible ability to put details in context and to pick out the occasional gem from my often rambling stream of consciousness. Maria believed in me even when I gave her reasons not to, especially regarding my use of commas. And over the course of my time here, Maria has been a wonderful colleague, and dare I say, a good friend. I certainly like to thank my committee, Brad Osgood and Phil Scherer, for being with me here today and spending some of their precious time. And I've had the pleasure of speaking with and working with a variety of different VLF faculty during my time here, including Don Carpenter, Martin Walt, and Nikolai Latina. I'd certainly like to thank the VLF staff that have made this experience run more smoothly. In particular, Dan Muzatescu, who handles the very large quantities of data that I need on a constant basis without hardly any complaint. And our group engineer, Jeff Chang, and our group admins, Shaolin and Helen. I certainly wouldn't have had nearly as much fun here in the group without the help of a few different VLF group members, including Kevin Groff, who is currently in Antarctica, perhaps being eaten by an Antarctic snow monster. But if not, I promise to show him the video of this to bore him to tears later. Forrest, David, Dennis, Ryan, and Morris, I've had the pleasure of working with, as well as certain VLF group members who have moved on to perhaps even better places, including Brandt, Projwell, and Mark. I have to thank my interactions with the Stanford Triathlon and Stanford Cycling teams, with whom I've had the pleasure of spending my perhaps exorbitant time outside the group. And I certainly have to thank my family for being here today, for making the long trip from New York, New Jersey, and Austin, Texas, and Boston, Massachusetts, including my parents, my sisters, and my grandma. Finally, this defense wouldn't have been nearly as interesting or as much fun without the help of my wonderful wife, Rachel, who has been both beneficial to my time here with her love and support, and also detrimental because she's made leaving the office early that much more appealing. Without Rachel's help, I probably still would have gotten a PhD, but it certainly would have been a lot less fun. Now, it's difficult and perhaps even callous to summarize 5 years' worth of research in a single 5-line limerick, but I'll do it anyway. And this is entitled A Poem About Research. There once was a chorus display about which Umran did say, "Analyze this for years till a pattern appears, and I'll sign your thesis that day." Now, it's traditional here to leave you with my contributions, but as a seasoned Antarctic traveler, I feel like it is really my duty to leave you instead with a public service announcement, where if you ever find yourselves in Antarctica, for example, to repair and maintain VLF equipment, it's important to bear in mind at all times that Antarctica truly is the coldest, harshest continent on the planet, and you should always act and dress appropriately. Thank you.